Good morning, everybody. Thank you for joining the webinar. We're going to give the last few registrants a chance to join. And I'll start this up in 1 minute. Thank you. Okay, I'll get going now. Everybody, thank you for joining today. This is Chris Cowan with Ozen Engineering. This is our weekly webinar that we've been doing, and today's topic will be patch antenna simulation by Stephen Liu. Just a brief introduction to our company. Ozen Engineering is a simulation-based company. We use finite element analysis and computational fluid dynamics to solve multi-physics, multidisciplinary engineering problems. I'm proud to say that Ozen Engineering was selected as the Ansys Channel Partner of the Year in this most recent year, and we're also certified as an Elite Channel Partner. As a channel partner, that means that we sell software, Ansys software. We provide training to the users and we provide technical support to the users. In addition, we provide engineering consulting services. If you have a project, we'll be happy to talk with it to tell you how we can help you by solving that using Ansys simulation tools. We work with the full suite of Ansys products, including fluids, electronics, structures, interactions between the different physics as multi-physics. In addition, there's optics, a new capability for Ansys this year. We have cloud services in different formats, either interactive or just batch submit, and we have tools for virtual reality collaboration. If you have any interest in those, please contact us. So our webinar schedule. Today's topic is patch antenna design. We have a couple webinars coming up so far scheduled for the next few weeks on structures and fluids. We have a history of webinars that you can see here dating back to November and beyond that. You can find those on our website. On our main page under resources, or you can type in the direct link, ozeninc.com/webinar library, to view previous recordings. You can register. We'll be happy for you to join us for any of these webinars in the future. You can reach those from ozeninc.com/training or on the home page of Ansys under events. And if you would like to receive notification by email about once a month, we send out a newsletter, and you can register for that on our website. So our contact information, please contact us if you ever have something you'd like to discuss related to Ansys simulation, either software or consulting. Our email is info@ozeninc.com, our phone number, and you can find everything on our webpage. I'd like to also announce that we are currently hiring a mechanical engineer and an electrical engineer. If you're interested or if you know a good candidate, please have them submit their resume through our website. So without further ado, I'm going to turn this over to Stephen, and he'll talk about patch antenna design.
All right, thank you, Chris. Let me start sharing my screen.
Okay, he's just getting his screen up right now, and I should just let you know, Stephen, he's an application engineer here at Ozen Engineering. He has his electrical engineering degree, BS, from UC Santa Barbara. If you're a customer of ours and you call for technical support related to electronics products, you'll be speaking with Stephen about that. So it looks like your screen's up and going, so I'll sign off here and let you take over.
Thanks again, Chris. So today's webinar is about patch antenna simulation in Ansys Hfss, and I'll just go through a typical demo in HFSS. This example is intended to show you how to simulate and analyze a microstrip antenna using Ansys Hfss, and it will show you how to generate the S parameter plot as well as the radiation pattern on the patch antenna. So here I have the Ansys electronic desktop opened up with an HFSS design open, and also I have imported a geometry of the patch antenna we are trying to simulate. So just give a brief introduction on this patch antenna. It's so we're trying to analyze this geometry from 8 gigahertz to 12 gigahertz. The antenna itself resonates at 10 gigahertz, and it is fed through a transmission line that at this port with a 50 ohm port impedance. The dimension of this patch, the substrate is 2.3 centimeter by 2.93 centimeter, and the antenna is about the square here is about 1 centimeter by 1 centimeter. The thickness of the substrate is 31 mil, right, as you can see here. So with the if you were to simulate a geometry like this, you are welcome to do the drawing in electronic desktop on your own, or you can just import a geometry that you have already. So in today, I'll just to save the time, I'll just have it imported. So before we start, we want to set up the solution type for this kind of simulation. Here we want to set up this for driven terminal, and the driven options is network analysis. The difference between driven model and driven terminal is that driven model is field-based transmission line interpretation, while the driven terminal is circuit-based transmission line interpretation. After setting up the solution type, we want to assign some material to our geometry. So first, we want to give a material to the to our substrate. We can, for this one, we'll add a new material for it. Let's name it my sub, and we'll give a permittivity value of 2.2, and you can click OK on it, and my sub is available for you. Since there's only one solid, as you can see, we have a substrate here, and we have a ground plane, and then there is just a sheet of the patch, and then the port is here. So there's only one solid, one actual solid in this geometry, in this model. So this will be it for the material assignment. Next, we'll give some boundary conditions on the patch and the ground plane. So we will go to add it and select objects by their name. Here we'll select ground and patch. Then we go to HFSS boundaries. We assign a finite conductivity boundary condition. We'll leave everything as default. Once you have assigned a boundary conditions to it, you will have that in your project tree, a project manager on the tree, the project manager on the left. Next step, we want to create an open region where determines the domain where that HFSS will simulate in. We go to HFSS model and create an open region. As we mentioned before, this antenna runs at 10 gigahertz, so the operating frequency will be 10 gigahertz. Under the boundary, we want to select perfect PML, stands for perfectly matched layer. It's a lossy anisotropic material which fully absorbs electromagnetic fields. We'll click OK on that. After clicking OK, you will see that there's a box created around the model. So that will be this will be our simulation domain. Next, we want to assign do the port setup. Same procedure. We go to Edit, and we select objects by name. We click on port. Then same procedure. Go to HFSS excitation. We assign a lump port. While creating the lump port, it will ask you what's your reference. What will be your reference reference plane? We'll select ground. Anything when you're creating a port or when you're creating a lump port, any conductor that's connected to it will list it here, and it will ask you to choose which to choose as a reference for your port. So in this case, we choose ground. Then we want to set. So this is pretty much it for excitations and boundary. The next step, we'll set up a solution setup. We go to HFSS analysis setup. We add a solution setup. We call it setup 1, and we want to set the solution frequency at 10 gigahertz. Maximum number of passes determines since Ansys electronic desktop or the electronics products, we use a technology called adaptive meshing. That is a technology allows the mesh to generate automatically and refine itself on its own through the passes. So the number of passes determines how many iterations it will refine itself. So the maximum will be 6, but it will stop if it converges. So if the solution converges at three passes, then the simulation will stop. Here we'll just set it to be 6. The maximum delta S will have it to be 0.02. Then we go to the option tab. We want to have the solution options to set it to mixed order. So this is usually advised for first-time simulation. And we want to have iterative solver. relative residual, we'll leave it as what it is. We click OK on it. Setup 1 is available now under analysis. After that, we want to add a frequency sweep to this analysis. So we want to right-click on Setup and add a frequency sweep. We want to have the option. We want to have the sweep type to be interpolating. Why interpolating? Because it adaptively determines discrete solver points using the adaptive mesh that I just mentioned, so that in the matrix data, so that a matrix data will be available for every frequency in the sweeps, and the field radiation pattern will be available as well at the last adaptive solution. So we wanted the distribution to be a linear step, starting at, as we said, starting at 8 gigahertz to 12 gigahertz. The step size, we want that to be 0.01 gigahertz. So this will be all frequency points in the simulation. Then we click OK on it. So now we can hit on, everything is ready. We can hit on Analyze under simulation. Before we hit Analyze All, we can always validate your setup and your model. If all the things are having a green check, you're good to go. So we'll hit on Analyze. To save some time, I'll open an identical project with their results available already. So this is a simulated project, same project. So first we want to create a 2D rectangular plot for the S parameter. The way how to plot it is we right click on results and go to create terminal solution data report, and then click on rectangular plot. So we'll leave the solution for the sweep. The domain will be sweep as well. And we go to the terminal S parameter. This S1. This is basically S11. Is that where we're interested? So we can see at around 10 gigahertz. This is where the patch antenna resonate. We can also plot the field overlay, the electric field on the actual geometry. The way how to do it is we go to, first we want to select the face on. So we want to see the electric field distribution on the surface of this patch antenna. Before that, let me turn off this 2D radiation pattern first. Okay. So we want to select the face of the upper face of this geometry. You can do so by go to Hfss. By go to Edit and select mode, and you can click on face. Or as you can see here, you can simply click F on your keyboard. So that will be a face selection. And then we can either right click or go to HFSS under fields. We want to plot fields, E and the magnetic E. We'll use the solution. Last adaptive is the only solution available. Then we'll click done on this. Then we'll have a E field plotted on our model. You're always welcome to change the legend on this. We can go to scale. We can double click on the legend and go to scale to adjust your legend. Here we can change that to. This is already in log form. So this will be our E field. Then we can also plot a 2D radiation pattern that shows us the gain of this patch antenna. To do it, we can first let me turn off the E field. And just a little useful tip for maneuvering auto models and plot radiation patterns. You can click on this little eye on this eye on a table, and then upon clicking it, you'll be able to select and deselect the visibility of your 3D model, your color keys, your E field, your boundaries, your excitations, and as well as the field reports you created. So we're trying to create a 2D radiation pattern here. We go to HFSS radiation, insert far field setup, and we want to have an infinite sphere. So this panel is asking you to give the dimension of the pattern that you're trying to. So here you specify the phi and theta value. So for phi, we want to do a full 3D 360 sweep on the radiation pattern. So we start it with 0 degree, and then we stop at 90 degree. Step size will be 90 degree. For theta, we'll sweep it from negative 180 to stop at 180 degree. Step size will be 2 degree. And we click on OK. Then we create reports on the antenna. We go to HFSS results, create far field reports, and we want to choose radiation pattern. So the geometry will be the one that we just created, infinite sphere. And then we choose gain, total gain, and we want this to be presented in decibel. Then we click on a new report. This will be our 2D radiation pattern on the antenna. We could also have this being overlaid on the model as we did already. Next, we want to plot a 3D pattern, a 3D field overlay radiation pattern. So same ideology. Before that, we want to define a infinite. We wanted to find a domain as well. So we go to HFSS radiation, insert far field setup, infinite sphere. we'll call this infinite sphere. Let's call this infinite sphere 2. So the sweep will start from 0 to 360. Step size, let's say 5. We'll, for theta, we'll start at 0, stop at 180 degree. Step size will be 2. Then we go to HFSS results, create far field report, and here we click on 3D polar plot. Create here, far field 3D polar plot. We choose infinite sphere and everything. We'll choose gain, total gain, and also we wanted this to be in decibel. So now we have a 3D radiation pattern presented. So this looks like a very nice. So we can see we'll have a gain about 10 at the maximum peak. So we can also same as the 2D radiation pattern. This 3D radiation pattern can also be overlaid on our actual model. So we go to HFSS 3D modeler, 3D model editor. Then under fields, I want to plot fields. I want to plot radiation field. The plot that we just created, I believe it should be plot 5. And before you apply it, you can always scale it and set the transparency of the pattern. So here we can have this overlaid on our actual model. So yeah, this would be the steps to simulate a patch antenna and have the S parameter and the radiation pattern plot. If you have any questions, please raise your hand. Or you can type it in the question section. Okay, it seems well, this example is fairly straightforward, and there's also related material or tutorial on this topic. So if anyone is interested, feel free to contact us, and we can talk more about this or share the material with you. Other than that, this will be it for today's webinar. Thanks everybody for attending, and have a nice day.